Hello AP Physics students, this is Mr. Evely talking to you. I'm in Lansing today, so I recorded this lesson for you. The new unit after our forces unit is going to be energy. Kinetic energy and work is the first chapter, chapter 7, and then chapter 8 gets into potential energy. So let's get started. Okay, the first thing we have to do, strangely enough, is to define what kinetic energy is. This is a different approach than last year. Last year we started with work, and from work we defined kinetic and potential energy. Your book kind of takes a different approach, but it's not a bad approach. It's just kind of interesting in that we just assume we know what kinetic energy is right off the bat. So the first thing we're going to do is define kinetic energy as the energy that an object has by virtue of its motion. If an object's in motion, it's got kinetic energy, just like last year. What's different from last year is we will assume that kinetic energy is 1/2 the mass times the velocity squared, without deriving it. This is the definition of kinetic energy. Question: is kinetic energy a scalar or a vector? Answer, since I don't have any students in front of me, the answer is that it's a scalar. It doesn't have direction. Kinetic energy is directionless. Can kinetic energy ever be negative? Well, check it out. The velocity here is squared. So if the velocity is squared, even if the velocity is negative, it turns out kinetic energy will always be positive. Kinetic energy is always a positive quantity. What are the units of kinetic energy? We measure kinetic energy in units of joules. Okay. We can also measure it in other units like electron volts, but we'll get to that stuff later. For now, it's units of joules. Okay? All right. Next. Suppose an object has a mass of 5 kilograms and is traveling at a velocity of 4i hat plus 9.0 j hat meters per second. Find its kinetic energy. Okay, we can find the kinetic energy a couple of ways. We could say on the x-axis it's moving at 4 meters per second, so we could say, okay, kinetic energy 1/2 mv squared is equal to 1/2 the mass, 5 kilograms, times 4 meters per second squared. We could then calculate that answer and then do it for the other axis. So on the y-axis, we can calculate this to be 1/2 mv squared, or 1/2 times 5 kilograms times 9 meters per second. Okay, so a quick calculation. Gives us 40 joules for the x-axis, and 0.5 times 5 times 9 squared gives us 202.5 for the other axis, for a total kinetic energy of 242.5. Round that off to 2 sig figs, we call it 240 joules. Okay? Why can we take the x kinetic energy and the y kinetic energy and just add them together? Because kinetic energy is not a scalar. I beg your pardon, because kinetic energy is not a vector. It's a scalar. So since these are scalar quantities, let's just add them up. Okay? Get the total result. But that means it should work another way too. If we find the magnitude of this velocity and stick it into the equation, it should also work. So, in other words, this represents 4 meters per second on the x-axis while being 9 meters per second on the y. The magnitude of our velocity then is 4 squared plus 9 squared. Take the square root. Okay, magnitude of velocity is 9.848. Let's call it 9.85. Okay, so it's moving in this direction at 9.85 meters per second. Kinetic energy is 1/2 the mass times v squared. So take my answer, square it, multiply by 1/2 of 5, and guess what? We get 242.5. Okay, it can't matter. Because once again, kinetic energy is a scalar, not a vector. We get the same answer whether we add up the kinetic energies on each axis or if we just take the magnitude and shove it into the equation, we should get the same answer. It's really convenient that kinetic energy is a scalar, not a vector, because it makes it easy to deal with mathematically. We can add things up and deal with it in a very simple way compared to other things like velocity and force and so on. All right. Moving on, what we need to do is think about what it takes. Here we go. What it takes to give something kinetic energy. Like if I pick up a ball and I throw it across the room and give it a certain amount of kinetic energy, that requires a force. I have to give it an initial velocity. That means I have to apply that force over a specific distance. So when we dealt with that last couple chapters, we'd say, okay, if I gave it some final velocity, that the relationship between that final velocity and the initial velocity is this, which you recognize just as the time-independent or space-band-spiff equation. Now, if I do something very strange, which is to multiply both sides of that equation by 1/2 the mass of the object that I'm throwing, the ball or whatever it is, I get a really weird result. So watch this. Multiplying both sides by 1/2 m, it seems like a strange thing to do, but what it tells me is that the final kinetic energy of the object equals the initial kinetic energy object plus this strange quantity over here, ma delta x. Now we recognize ma as mass times acceleration, which any good physics student knows is the sum of all forces acting on the object, times delta x. So if I want to change the kinetic energy of an object, I have to apply a force to it over a distance delta x. So we give this quantity a special name, we call it work. If I want to increase or change the kinetic energy of an object, I have to do work on it. So if I toss this over to the other side, I get the change in kinetic energy of an object equals the sum of the work done on that object. Okay, we're defining work as force times change in position or displacement. This is called the work kinetic energy theorem. With the work kinetic energy theorem, we can define all of energy without resorting to potential energy. We could say, all right, if I toss a ball up into the air, gravity is going to do negative work on it, so it's going to slow down. How do I know it's negative work? The force is down while the displacement is up. So on the way up, the ball has a force this way and a delta x this way. Okay? And what's happening? The kinetic energy is decreasing. On the way back down, the ball has a force down and has a delta x down. So that's positive work. Whenever gravity does positive work on something, the change in kinetic energy is positive. Now, on the way up, gravity does exactly the same amount of negative work as it does positive work down. So when I end up with the ball in my hand, when it's done, gravity has done net zero work. So it has the same kinetic energy when it hits my hand as it did when I left it. So the work kinetic energy theorem allows us to come up with this relationship between force and energy. So we can relate everything we did in the last couple chapters with what we're doing now, with this equation here. This is the bridge between the two. Okay? So, let's do a couple of examples, and my short video will be complete. So let's see. There we go. Example, a block of mass 4 kilograms is dragged 2 meters along a horizontal frictionless surface by a force of 30 newtons, acting at an angle of 53 degrees to the horizontal. The initial speed of the block is 3.0 meters per second. Find the change in kinetic energy of the block and its final speed. All right. So, diagram. We've got a block sitting on a surface. We've got a force acting on it. Angle is 53 degrees. Force is 30 newtons. Okay? The mass of the block, 4 kilograms. Delta X, 2 meters. Okay? Initial speed, 3 meters per second. Okay. Now, if we want to find the change in kinetic energy of the block, one way to do it would be to figure out the acceleration of the block over that distance of 2 meters. We could calculate the final velocity and then use that to get the change in kinetic energy, or we could just calculate the work done on the block. The work done on the block, the sum of all the work, is equal to the change in kinetic energy. So if that's true, I should be able to do that. The thing is, force is a vector. So we have to kind of be careful about the work being done. The force is at an angle of 53 degrees. The displacement is horizontal along the ground. If we're going to calculate the work, we need to calculate the amount of force in the direction of displacement. In other words, I'm going to take this force and break it down into 2 components and say, look, F cosine theta is the amount of force that is in the direction of motion. So that's actually adding to the kinetic energy of the block. The other component, F sine theta, we're going to discard because it is perpendicular to the direction the block is moving. It's not doing anything to change the kinetic energy of the block. It's not enough to lift the block. So we're going to calculate the work by taking those 2 quantities, F cosine theta and delta x, and multiplying them together. So the sum of the work, in this case, is going to be F times delta x times the cosine of theta. Okay? Now this is a reoccurring theme in calculating work. You need the force, you need the displacement, and you need the cosine of the angle between those 2 vectors, between F and delta x. It's so common that they call it, I have a special name in math, they call it a dot product. So in other words, work is the dot product of force and displacement. If these 2 guys are vectors, when we multiply them together, we take the force and the displacement, their magnitudes, the size of the force and the size of the displacement, and we multiply by the cosine of the angle between them. So it's just kind of a thing, not just in physics, but in math. It's called the dot product of 2 vectors. Later on, we're going to multiply two vectors together and get a vector out of it. Okay, that's going to be a few chapters from now. That's called a cross product. So there's two ways to multiply vectors. This is one of them. All right, back to the problem. We've got a force of 30 newtons. We have a displacement of 2 meters. We're going to take the cosine of 53 degrees and punch this baby out. And I just misplaced my calculator. I set it down. There we go. So 30 times 2 times the cosine of 53. Doing this in degree mode instead of Stoughton mode, we get like 36.1 joules of work. Which means the kinetic energy went up by 36.1 joules. Okay? So next, we want to find the final speed of the block. How are we going to do that? Well, what we need to do is calculate that final velocity based on this change in kinetic energy. There's a couple ways we could do this. One is to find the initial kinetic energy and add it to this change, get the total kinetic energy. And from the total kinetic energy, the final kinetic energy that is, we could calculate the final speed of the block. Okay? Another method is to write the equation and do some algebra to solve for V final. But I think this kind of makes sense. If we say, all right, this is the change in kinetic energy. The initial kinetic energy is 1/2 mv naught squared. Okay, it's got a mass of 4 kilograms again. Initially moving at 3 meters per second. Okay, so we got half of 4 times 9. Sounds like it's going to be 18. Okay, so 18 plus 36.1 is going to yield us 54 joules or 54.1 joules. I'm running out of room. Let's see. I'm going to make a little space here. Okay. There we go. So total kinetic energy, or should say final kinetic energy, 54.1. Final kinetic energy is 1/2 mv final squared. So what we're really after is the final velocity. So we'll say 2 times final kinetic energy divided by the mass, take the square root, should give us the final velocity. So punch those numbers in. I don't have too much room to write them, so I'm going to say 2 times my 54.1 divided by 4 kilograms and take the square root. So it yields about 5.2 meters per second. So it initially was moving at 3 meters per second. In the end, 5.2 meters per second. The gain in kinetic energy was caused by us doing a work of 36.1 joules on the thing. Okay? So in other words, in order to change the kinetic energy by 36.1 joules, we have to do 36.1 joules of work on the object. That's how they're connected. All right. Go. Come on. There it goes. All right. A runaway crate of prunes slides over the floor toward you. To slow the crate, you push against it with a force of 2.0 newtons I hat minus 6.0 newtons J hat while running backward. While you push it, the crate goes through a displacement of and I'm using D here for the displacement instead of X because this is two-dimensional. Negative 3.0 meters I hat plus 0.50 meters J hat. how much work has your force done on the crate during the displacement? Okay, now one way to do this is to calculate the force and its angle, calculate the displacement and its angle, then multiply the magnitude of the force, the magnitude of the displacement, and then multiply by the cosine of the angle between them. And that's going to get messy because the force, neither the force nor the displacement are on any of the axes. So this gets a little weird. What we're going to do instead is a technique of dot multiplication when we're in unit vector notation. So it makes it a ton easier to solve these problems when they're in unit vector notation. So here's the deal. Okay, work is going to be the dot product of these two. Okay, so I'm going to say it's going to be 2I hat minus 6J hat for the force. And forgive me for dropping the units here. I'm just going to make an illustration to show you what you do in a case like this. I'm dotting this with negative 3I hat plus 0.5 J hat meters. Okay? If it really bothers you, put newtons here, meters here. Life is good. We've got units. Now, you can multiply these two guys together using the FOIL method, first, outer, inner, last. But there's something kind of cool that happens when you do this. So let me just do it real quick. I'm going to say, all right, 2I hat times the negative 3I hat, that's going to be negative 6. And this is a dot product, which means that these two components are in the same direction, or they're both on the x-axis, which means the answer is just plain old 6. Remember, when you calculate work, you've got a scalar. Okay? All I did was multiply this guy and this guy. Okay, then we do the outers. We say, okay, I'm going to multiply the 2I hat by this guy. Now keep in mind, I hat and J hat are perpendicular to each other. So if I have 2 times 0.5, and then I multiply by the cosine of the angle between them, I'm going to get 0. Okay? Notice when I did the 2 and the negative 3, they were in the same direction. So I had 2 times negative 3 times the cosine of 0 degrees, which gives me negative 6. Now I've got 2 in the x direction, 0.5 in the y direction. The cosine of 90 degrees is 0. So when I multiply those two guys together, I actually get 0. Okay? The next step is to multiply the inners, this guy and this guy. But we encounter the same thing. The j hat and the I hat are perpendicular to each other. So I could take negative 6 and multiply by negative 3, and then multiply by the cosine of the angle between them, and I still get 0. Next step is multiply last. First, outer, inner, last. So I've got negative 6 times 0.5. That's going to be negative 3. Multiply by the cosine of the angle between them. They're both pointing on the y-axis, so the angle between them is 0 or 180 degrees in this case, but the cosine basically gives us negative 3. So I'm going to say negative 6 times 0.5 times the cosine between them. Guess what? Negative 3. Answer, negative 9. Okay? And the units are joules. And I am done. Okay? So the moral of the story is, all I need to do is multiply the i's together. I get negative 6. Multiply the j's together. I get negative 3. I'm done. So the other part of the FOIL method that includes the outers and the inners just ends up being 0 anyway because we're dealing with vectors. With a dot product, we have to multiply by the cosine of the angle between them. So it's a little strange, but once you get used to it, it's really fast. So the answer is 9 joules. So how much work has your force done? 9.0 joules of work. Oh, I beg your pardon. You've noticed already, it's negative 9 joules. So we're going to slow the crate down. We're reducing the kinetic energy by 9. I apologize. We do need to have that negative sign in there. So if the crate has a kinetic energy of 10 joules at the beginning of the displacement, what's its kinetic energy at the end? All right, well, the total work equals the change in kinetic energy. So we've lost 9 joules, so we're down to 1 joule. So K final is 1 joule of kinetic energy. Okay? If they wanted us to, we could find the new velocity by taking 1/2 mv squared and solving for v. All right, so the main thrust of this particular example is to show how to get the work if we have this thing in unit vector notation. If you think back to the Camtasia videos on vectors, remember I did a little bit of this when we talked about multiplying vectors together. Okay. This one's kind of a crazy problem. Unfortunately, I don't have a lot of room to write here. But the idea here is the luggage handler pulls a 20-kilogram suitcase up a ramp that is inclined at an angle of 25 degrees above the horizontal with a force of 145 newtons. It acts parallel to the ramp. The coefficient of kinetic friction between the ramp and the incline is 0.3. If the suitcase travels 4.60 meters along the ramp, calculate the work done by all these different forces. Okay? So, let me move this out of the way. Let's get into writing mode here. Okay, this looks good. All right, so got this ramp. I've got a suitcase on it. Let's see, we've got weight. We've got the force that's being applied to the thing. We've got the normal force. And let's see, we've got friction as well. Okay? So the first thing is, how much work is done by our force? Well, the displacement is up the incline. So there's our delta x, so to speak, and it is a delta x of 4.6 meters. So the first one is not too bad. We're going to say the force and the displacement are in the same direction. The force is 145 newtons. So here we go. The work done by the applied force is going to be that applied force times delta x. They're in the same direction. So the cosine of 0 degrees is 1. Life is good. 145 times 4.60. Okay? The answer is 667 joules for part A. Next, the work done by the suitcase by the gravitational force. Okay. Now, the angle of the ramp is 25 degrees. So we know this angle. So we could do this a couple ways. We could take that weight force and break it down into two components and calculate the work done by each component. Or we could take the work equation at its word and say, okay, the work done by the weight force is equal to the weight force times delta x times the cosine of the angle between the weight and delta x. So check it out. We're talking about this angle right here. So if the angle of the ramp is 25 degrees, what we're going to do is add on 90 degrees and get 115. So literally, we can say, all right, it's a 20 kilogram suitcase, so I've got 20 kilograms times 9.80 meters per second squared times 4.60 meters times the cosine of 115 degrees. Okay? So trusting the equation for a moment, 20 times 9.8 times 4.6 times the cosine of 115 gives us an answer of negative 381 joules. Okay? Now, that kind of makes sense. The component of the weight force would be down the incline, which is opposite the direction we're moving, which means gravity is busy taking energy away, taking kinetic energy away from the system. The work done on the suitcase by the normal force. Now, the normal force, if we do force normal times delta x times the cosine of 90 degrees, because the normal force is perpendicular to delta x, we're going to get 0. We're pushing this thing up the incline. The normal force is doing nothing to change the kinetic energy of the suitcase. Answer, 0. 0 joules, I should say. Okay? Next, the work done by the frictional force. Now, the frictional force is going to be kind of a pain because, for one thing, it's opposite the direction of displacement. It's going to take energy away from the system, which kind of makes sense. Friction, removing energy from the system. We're also going to need to figure out the normal force because they gave us the coefficient of friction. So if you forgive me a little bit of jumping ahead, we're going to say, all right, work done by friction is equal to the frictional force times delta x times the cosine of the angle between them. Okay, now frictional force is going to be mu times mg cosine theta. Okay, then I'm going to take delta x and multiply by the cosine of 180 degrees. I have to be careful here. This theta is different than the theta we're talking about in the mg cosine theta. So the angle between f of x and delta x is 180 degrees. What that will do is turn our answer into a negative answer, like we expected. So, mu, let's see, we have a mu of 0.3, a mass of 20 kilograms, times 9.8 meters per second squared, times the cosine of 25 degrees, times our delta x, which is 4.6, times negative 1, the cosine of 180 degrees. So let's see if I can punch this all in correctly. 0.3 times 20 times 9.8 times the cosine of 25 times 4.6 times negative 1. The answer is negative 245. Okay, that's the answer for part D. Part E is the total work done on the suitcase. So in other words, I'm going to take all of these answers and add them up. So I've got 667 plus 0. Oh, sorry, I forgot. Minus 381 plus 0 minus 245 means we've got 41 joules of positive work getting done. Okay, so an additional 41 joules was added to the suitcase the suitcase starts from rest, we'll say. So 41 joules of work means 41 joules of kinetic energy was added. So if we want to find the speed of the suitcase at the bottom of the ramp, I beg your pardon, find the speed of the suitcase at the top of the ramp, we're going to say, all right, K equals 1/2 mv squared. Okay. We're assuming the initial kinetic energy is 0 here. That's kind of important. So V final equals 2K over m, and take the square root. So I've got 2 times 41 joules of additional kinetic energy divided by a mass of 20 kilograms. So 82 over 20. Answer 4.1. Take the square root. And we've got 2.02 meters per second. Looks like we get 2 sig figs on this, so I'm going to say 2.0 meters per second. Okay, now I didn't quite have room to show it, but I could take that calculation kind of simply because the initial kinetic energy was 0. If the initial kinetic energy wasn't 0, I'd have to add our additional 41 onto the initial kinetic energy. Then I could calculate the final velocity. But since the initial was 0, I could go straight to the answer using the definition of kinetic energy. So keep in mind this was final kinetic energy I had there. And that's what I need in order to calculate final velocity. So I hope some of this stuff made sense. It at least gives you an introduction to energy. And of course, if you've scratched your head through any of this during the presentation, I will be here to answer questions later this week. Tomorrow's the test, so be sure to come in Thursday morning with your questions, and I can answer them as best I can, and we'll do our best to take the test then Thursday morning. So hope you're having a good day. I'm in Lansing, hopefully having a good day talking to the governor and some representatives. I'm signing out. This is Mr. Evely, AP Physics. Talk to you later.